It's very good to have you here. Tonight we're asking one of those questions that feels simple for about half a second, and then immediately begins to unfold into something much larger. What lies beyond the edge of the universe? Before we go anywhere, a small and honest aside. These videos stay free of ads, which is really the whole point of the quiet, and what makes that possible is the ebook. So if the mood takes you, and only then to wander over and have a look. Quantum physics, explained clearly, is the channel in book form. The same ideas, unhurried, laid out with the patience they deserve, and the full narrated audiobook comes along with it. There's a QR code resting on screen if you'd like it, and the address, thesleepyscientist.com, is sitting quietly in the description. A look really is the kindest thing you can do to keep these evenings going. That's the whole of the ask, and I mean it gently. Thank you. Now, before we drift too far towards the edge of everything, let me know where in the world you're listening from, and what time it is for you. It's always lovely to imagine this little corner of science reaching people at different hours, in different places, under different skies. It's a question that almost invites the imagination to draw a picture. A vast sphere of galaxies, glowing softly in the dark. A final border somewhere beyond the most distant stars, and then, beyond that, perhaps nothing at all. Or perhaps another universe. Or perhaps some strange outer darkness that makes ordinary darkness look rather sociable by comparison. But as we'll see, the universe doesn't seem to have an edge in the way a table, a planet, or a map has an edge. The boundary we can observe isn't a wall where space stops. It's a horizon created by the finite speed of light, the age of the universe and the expansion of space itself. The farther we look, the farther back in time we see, until we reach the oldest light available to us, the cosmic microwave background, the faint afterglow of the early universe. And beyond that visible horizon, the most careful scientific answer may also be the most quietly astonishing one. There may simply be more universe, more space, more galaxies, more vast filaments of the cosmic web, more regions of reality whose light has not reached us, and perhaps never will. So get comfortable, let your thoughts slow down, and allow the question to open gently. Because tonight, we're not travelling to the edge of the universe to find a wall. We're travelling there to understand why the edge may never have been a wall at all. We picture it so easily. The universe as a vast glowing sphere, suspended in a darkness even larger than itself. Inside the sphere are galaxies, stars, nebulae, planets, black holes, dust, radiation, and every quiet corner of cosmic history. Outside it is something else, perhaps emptiness, perhaps another kind of space, perhaps an even deeper darkness waiting beyond the final rim. It is a natural image. In some ways it is even a comforting one, because it turns the universe into something the mind can hold, a shape, a container, a thing with an inside and an outside, a thing that, however enormous, still behaves like the objects we already understand. But scientifically, that image is misleading. The universe is not known to be a giant object floating inside a larger dark room. It is not known to have an outer surface, like a planet, a bubble, or a balloon. When cosmologists talk about the universe, they are usually not describing something placed within space. They are describing space itself together with time, matter, energy, radiation, dark matter, dark energy, and the physical laws that connect them. That is where the question begins to change. In everyday life, edges are everywhere. A room has walls, a table has sides, a book has covers. A country has borders drawn on maps, even if the land itself does not politely glow at the line. Planets have surfaces, oceans have horizons, roads appear to narrow into a vanishing point. Our senses are trained by boundaries, because the world we live in is full of objects that end. So when we turn our attention to the largest thing there is, we naturally ask where it ends. This instinct is not foolish. It is one of the reasons human beings can think at all. We understand the unfamiliar by borrowing from the familiar. If a house has walls, perhaps the universe has walls. If Earth has a surface, perhaps the cosmos has a surface. If a map has an edge, perhaps reality itself has one too. The problem is that the universe may not belong to the same category as those things. A planet is an object inside space. A room is a region inside a building. A map is a representation drawn on a surface. But the universe, in the broadest physical sense, is not one item among other items. It is the whole arena in which items exist. It includes the distances between galaxies, the passage of cosmic time, the radiation left over from the early universe, and the geometry that determines how motion and gravity behave. This is why asking what the universe expands into can be so tricky. It sounds like a simple question because expansion usually means something growing into a surrounding area. A balloon expands into the air around it. A cloud expands into the sky. A drop of ink expands through water. Every ordinary example of expansion seems to require a background space already waiting there. But cosmic expansion is different. In modern cosmology, space itself expands. The distances between faraway galaxy clusters increase because the scale of space changes over time. The galaxies are not all flying outward from one central blast point into empty surroundings. Rather, the fabric of large-scale space is stretching, so that distant regions become more distant from one another. Asking what space expands into may therefore be like asking what is north of the North Pole. The words are understandable, but the question smuggles in an assumption that may not apply. North is a useful direction almost everywhere on Earth, but at the North Pole the idea reaches its limit. There is no farther north to go, not because a wall blocks the way, but because the coordinate system no longer works in that manner. The same may be true when we ask what lies outside the universe. If the universe means all of space and time, then outside may not name a place at all. It may be a word borrowed from rooms, boxes and landscapes, then stretched beyond its natural use. This does not mean the universe must be infinite. It does not mean scientists know the full shape of all reality. The real answer is more careful. Space may be infinite, extending without end in every direction. Or space may be finite, but without a boundary. Or the total universe may have a global shape too large and subtle for us to measure from our small observable patch. Albert Einstein's general relativity gives the framework for thinking about this properly. In general relativity, space and time are not fixed stages on which the universe performs. They are dynamic. They can curve. They can stretch. They can be shaped by matter and energy. Gravity is not simply a pull acting across a rigid background. It is connected to the geometry of space-time itself. That idea allows possibilities that ordinary imagination finds difficult. A universe might be finite in volume without having an edge. A useful, limited analogy is the surface of Earth. A traveller moving across Earth's surface can keep going without encountering a final edge where the ground stops. Earth's surface has a finite area, but no boundary line where the surface ends. Of course, the analogy is not perfect. Earth's surface is two-dimensional, while cosmic space is three-dimensional. Earth is also embedded in surrounding space, and the universe need not be embedded in any larger space at all. Still, the comparison helps loosen the grip of the simple picture. Something can be finite without having a border. Something can curve back on itself without requiring a cliff at the end. So the edge we first imagine begins to fade. There may be no final shell of galaxies. There may be no cosmic wall. There may be no last star sitting beside an infinite drop into nothingness. The universe may not be shaped like an object with an outside. Yet there is still a meaningful edge in cosmology. It is not necessarily the edge of space, it is the edge of what we can observe. Because light travels at a finite speed, and because the universe has a finite age, we can only see the region whose light has had time to reach us. That region is called the observable universe. Its boundary is not a physical surface, it is a horizon, and horizons are subtle things. They look like endings, but often they are only limits of view. The universe we can see is not necessarily the universe that exists. That sentence is simple, but it quietly changes almost everything. Because when we talk about the edge of the universe, we are very often talking about the edge of the observable universe, and the observable universe is not the same thing as the whole universe. The observable universe is the region of the cosmos from which light, or any other signal travelling at the speed of light, has had enough time to reach Earth since the early universe became transparent. It is the part of reality that has been able to send us information. It is not all of space, necessarily. It is all of space that has had time to announce itself to us. That distinction matters because light is fast, but not infinitely fast. In empty space, light travels at about 300,000 kilometers per second. Nothing carrying information can travel faster through space according to special relativity, the theory Albert Einstein introduced in 1905. Special relativity showed that the speed of light is not just the speed of one particular thing. It is a universal causal limit. It is woven into the relationship between space, time, motion, and information. On Earth, this speed feels almost instant. Light can cross a room in a tiny fraction of a second. It can travel from London to New York quicker than the brain can form a proper complaint about airport queues. But across the universe, even light needs time, a lot of time. Light from the moon takes a little more than 1 second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star system beyond the sun takes more than 4 years. Light from a distant galaxy may take millions or billions of years to reach us. So when we look outward, we are not only looking across space, we are looking backward in time. The universe is about 13.8 billion years old. At first, it might seem natural to assume that the farthest thing we could see would be 13.8 billion light years away. After all, if light has had 13.8 billion years to travel, perhaps the edge of visibility should be 13.8 billion light years from Earth. But the universe has not been sitting still while that light travelled. Space itself has expanded. This is the crucial part. Light from the most distant regions we can observe began its journey, when those regions were much closer to the matter that would eventually become our galaxy. While that light travelled, the space between us and its source stretched enormously. So the present distance to the farthest observable regions is much larger than the simple age of the universe measured in light years. The rough modern estimate is that the observable universe has a radius of about 46 billion light years. That means its full diameter is about 93 billion light years. This is one of those numbers that does not fit comfortably inside the mind. It is not just large. It is large in a way that makes ordinary largeness look like it has not really been trying. Yet even this huge region is not necessarily the whole universe. It is only the part from which light has been able to reach us since the universe became transparent. That boundary is not a wall. There is no known shell at the edge of the observable universe. There is no physical surface where galaxies stop and a cosmic fence begins. No telescope is expected to look far enough and find a neat sign saying, "End of universe, please turn around carefully." The boundary exists because of time, light, and expansion. Cosmologists often call this kind of boundary a horizon. One important horizon is the particle horizon. The particle horizon is the maximum distance from which light could have reached us by now. given the age and expansion history of the universe. It marks the limit of what can currently be observed in principle, not just with today's telescopes, but with any telescope obeying the same laws of physics. An everyday horizon gives a useful comparison. When you stand by the sea, the ocean appears to meet the sky at a distant line. That line looks like an edge, but it is not the end of the ocean. Ships do not reach it and politely drop out of existence. The horizon is a limit to your view, shaped by your position and Earth's curvature. The particle horizon is different in its physical details, but similar in spirit. It is a limit to seeing, not necessarily a limit to existing. Beyond the observable universe, there may simply be more universe. There may be more galaxies, more galaxy clusters, more vast filaments of the cosmic web, more dark matter, more radiation, more enormous voids, and more regions of space whose light has not reached us. The laws of physics may continue there in the same way they appear to continue here, although we cannot directly test regions forever beyond our horizon. This is the most important correction to the usual picture. The edge of the observable universe is not the edge of everything. It is the edge of our cosmic view, and it is not the same for every observer. If there were an astronomer in a distant galaxy, that astronomer would sit at the centre of their own observable universe. Their visible sphere would be centred on them, just as ours is centred on us. Some of their observable universe would overlap with ours. They might see galaxies that we also see, though from a different angle and a different stage in history, but they would also see regions that are beyond our observable limit. At the same time, parts of our observable universe would lie beyond theirs. This does not make Earth special. It makes observation local. Every observer has a horizon because every observer receives only the light that has had time to reach them. The observable universe is centered on us in the same way the visible horizon at sea is centered on the person looking. It tells us where we are observing from, not where the universe itself is centered. So when we ask what lies beyond the edge of the universe, the first answer must be careful. If by edge we mean the edge of the observable universe, then beyond it there is no reason to expect a wall, a drop, or a final emptiness. The most scientifically grounded expectation is quieter and more astonishing. Beyond the edge we can see, there may be more space, more time, more matter, more light still travelling, and more cosmic history forever hidden from our particular place in the universe. The edge is real as a limit of observation, but it is not known to be the edge of reality. Looking far away in the universe is never only a matter of distance, it is also a matter of time. Whenever we look at something in space, we see it as it was when its light began travelling toward us. Light is fast beyond ordinary imagination, but it is not instant. It crosses empty space at about 300,000 kilometers per second, which is quick enough to make everyday life feel immediate, but not quick enough to erase the enormous distances between worlds, stars, and galaxies. This means every view of the sky is slightly historical. The moon is close by cosmic standards, but even moonlight takes little more than 1 second to reach Earth. When you look up at the moon, you're seeing it not quite as it is now, but as it was just over 1 second ago. That delay is tiny, but it is real. The sun is farther away. Sunlight takes about 8 minutes to reach Earth. The warmth on your face began its journey from the sun several minutes before you felt it. If the sun changed in some sudden way, Earth would not know immediately. For about 8 minutes we would still receive the old sunlight, which is a mildly unsettling thought, though thankfully not one that needs adding to the morning routine. Nearby stars carry us deeper into delay. The nearest star system beyond the Sun, Alpha Centauri, is more than 4 light years away. Its light takes more than 4 years to reach us. Other bright stars in the night sky may be tens, hundreds, or thousands of light years away. Some of the stars visible to the unaided eye are being seen as they were before particular human empires rose and fell, before inventions were made, before familiar names had entered history. The sky is not a single present moment. It is a layered archive. Some of it is only seconds old. Some of it is minutes old. Some of it is years old. Some of it is ancient beyond human history. And when telescopes look beyond the stars of the Milky Way, this effect becomes one of the great tools of cosmology. A galaxy 1 million light-years away is seen as it was 1 million years ago. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. A galaxy 10 billion light-years away is not a present-day galaxy in our view. It is a galaxy from a much earlier era of cosmic history, when the universe was younger, denser, and filled with galaxies still forming and changing. So telescopes do not give us a simple map of where things are now. They give us a view through time. This is why deep-field observations are so important. The Hubble Space Telescope transformed astronomy by staring into apparently dark patches of sky and revealing thousands of distant galaxies hidden within them. These images show that even tiny regions of the sky contain a vast population of galaxies at many different distances, and therefore many different ages. Later, the James Webb Space Telescope extended this search into infrared light. Built by NASA with major contributions from the European Space Agency and the Canadian Space Agency, the James Webb Space Telescope was designed to study some of the earliest galaxies whose light has been stretched by the expansion of the universe. This stretching is called cosmological redshift. Light that began as ultraviolet or visible light can be stretched into infrared wavelengths during its long journey through expanding space. That is one reason the James Webb Space Telescope observes in infrared. It is not merely looking for faint things, it is looking for ancient light that has been stretched by the growth of the universe itself. The farther astronomers look, the earlier the cosmic era they study. Nearby galaxies show the universe in a relatively mature state. More distant galaxies reveal times when stars were forming rapidly, galaxies were smaller and more irregular, and heavy elements were still being built and spread by generations of stars. Even farther back, astronomers approach the period when the first galaxies and stars began to shine. This turns the universe into a kind of natural history book, written not on pages, but in arriving light. Yet this book does not continue backwards forever in ordinary starlight. Eventually, if we look far enough, we do not find older and older galaxies without limit. We approach a time before galaxies existed, before stars, before planets, before atoms had settled into the transparent universe we know. In the very early universe, matter was hot, dense, and ionized. Electrons were not yet bound into stable atoms. Instead, the universe was filled with a plasma of charged particles and radiation. Photons, the particles of light, could not travel freely for long distances because they were constantly scattering off free electrons. The young universe was full of light, but it was not transparent. It was more like a glowing fog, although even that phrase is far too gentle for a state of matter hotter than the surface of any star today. Light was trapped in constant interaction with charged particles. A photon could move a little way, then scatter again, then scatter again. Information could not simply cross the universe in clean straight paths. This creates a natural observational boundary. When we look far enough away, and therefore far enough back in time, we eventually reach the era when the universe became transparent. That happened about 380,000 years after the Big Bang, when the universe cooled enough electrons and atomic nuclei to combine into neutral atoms. Once neutral atoms formed, light could finally travel freely through space. That released ancient light still surrounds us today, We call it the cosmic microwave background. It is not the edge of space. It is not a surface where the universe ends. It is the oldest light we can see directly, the afterglow of the hot early universe, stretched into microwaves by billions of years of cosmic expansion. In every direction we look, beyond the galaxies and beyond the deepest visible structures, we eventually meet this ancient glow. This is why the edge of the observable universe is not like the edge of a table or the wall of a room. It is also a layer of time. The farthest visible boundary is not showing us a place where reality stops. It is showing us an earlier state of reality. It is a horizon made from distance, light travel time, expansion, and the changing transparency of the universe. Beyond that visible layer, there was still a universe. But ordinary light from that earlier time could not travel freely to us. The universe was too hot, too dense, and too filled with scattering particles for a clear view, so looking far away means looking back. And at the deepest distance our ordinary light can reach, the universe does not end. It disappears into its own glowing past. The oldest light we can see is not starlight. It is older than the first stars, older than the first galaxies, older than the Milky Way, the Sun, Earth, and every familiar object in the night sky. It comes from a time when the universe was still young, hot, dense, and glowing everywhere at once. This ancient light is called the cosmic microwave background. It is one of the most important discoveries in modern cosmology because it gives us a direct view of the universe as it was when light first began to travel freely through space, not from one star, not from one galaxy, from the whole early universe. Before this light was released, the universe was very different from the transparent cosmos we see today. It was filled with a hot plasma, a state of matter in which atomic nuclei and electrons moved freely rather than being joined together into stable atoms. Photons, the particles of light, were present too, but they could not travel very far in a straight line. Every time a photon tried to move through the early universe, it was likely to scatter off a free electron. It would travel a short distance, collide, change direction, then do it again, and again, and again. The universe was full of light, but it was not clear. It was bright in a deep physical sense, but impossible to see through. A useful comparison is fog, though ordinary fog is far too gentle. In fog, light scatters off tiny droplets of water, so distant objects become hidden. In the early universe, light scattered off free electrons in a hot plasma. There were no ordinary distant objects to see yet anyway, no stars or galaxies waiting behind the mist, but the principle is similar. Light could not carry a clean image across great distances. Then the universe expanded and cooled. As the temperature fell, electrons could finally join with atomic nuclei to form neutral atoms, mostly hydrogen and helium. This process is called recombination, although the name is a little misleading, because it was really the first major combination of electrons and nuclei into atoms. Once those neutral atoms formed, there were far fewer free electrons available to scatter light. At that moment, photons decoupled from matter. Photon decoupling means that light was no longer constantly interacting with charged particles. It could finally travel freely through space. The universe became transparent. The light released at that time has been travelling ever since, crossing the expanding universe for billions of years before reaching our instruments today. This happened roughly 380,000 years after the Big Bang. At the time, the light was much hotter and more energetic than it is now. But as the universe expanded, the wavelengths of that light were stretched. This stretching is a natural result of cosmic expansion. Light that once belonged to a much hotter glow has been stretched into microwave wavelengths, leaving behind a cold, faint radiation that fills the sky in every direction. Today, the cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. It is almost perfectly uniform, a soft afterglow from the early universe, cooled by the expansion of space itself. The story of its discovery is wonderfully human. In 1965, Arno Penzias and Robert Wilson were using a radio antenna at Bell Labs in New Jersey when they detected a persistent background signal. It seemed to come from every direction. They checked their equipment. They considered possible sources of interference. They even dealt with pigeons nesting in the antenna, which is a rather undignified supporting role in one of the greatest discoveries in cosmology. But the signal remained. Nearby, researchers at Princeton University were preparing to search for just such a relic glow from the early universe. And decades earlier, Ralph Alpha, Robert Herman and George Gamow had worked on the theoretical idea that a hot early universe should leave behind radiation, cooled and stretched by expansion. Penzias and Wilson had found that relic radiation. The cosmic microwave background became powerful evidence that the universe had once been hot and dense. It strongly supported the Big Bang model, not as an explosion into empty space, but as the expansion and cooling of the universe from an earlier, much hotter state. Later, spacecraft mapped this ancient light with extraordinary precision. NASA's Cosmic Background Explorer confirmed that the cosmic microwave background has the expected spectrum of radiation from a hot early universe. NASA's Wilkinson Microwave Anisotropy probe measured tiny differences in temperature across the sky. The European Space Agency's Planck satellite then mapped those variations in even finer detail. Those tiny variations matter enormously. The cosmic microwave background is not perfectly smooth. Some regions are slightly warmer and some are slightly cooler by only tiny fractions of a degree. These differences show small variations in density in the early universe. Slightly denser regions had a little more gravitational pull. Over immense stretches of time, gravity amplified those small differences, helping matter gather into the first stars, galaxies, galaxy clusters, and eventually the vast cosmic web. So the cosmic microwave background is both an ending and a beginning. It is the end of how far back ordinary light can show us directly. But it is also the beginning of the visible universe as we can observe it, the first freely travelling light, carrying the faint pattern from which later cosmic structure grew. This is why the cosmic microwave background is often treated as the edge of the visible universe. But it is not the edge of the universe itself. It is not a wall in space. It is not a shell where reality stops. It is a surface of last scattering, a boundary in time marking the moment when the universe became transparent. Beyond it, in the earlier universe, ordinary light could not travel freely to us. The universe existed, but it was hidden behind its own hot plasma. The edge of what we see is therefore partly a wall of time, not a wall of space. When we look toward the cosmic microwave background, we're not seeing the final border of existence. We're seeing the oldest light that the universe allows us to receive directly. Beyond that glow lies not nothing, but an earlier, hotter, denser state of the cosmos, one that must be studied through physics rather than ordinary sight. The universe does not end at the oldest light. It simply becomes harder to see. One of the most common misunderstandings about the universe begins with a picture that feels completely reasonable. A tiny point appears in empty darkness. It explodes. Matter rushes outward. Galaxies form from the debris. And somewhere, if we could trace everything backward, we might find the place where it all began. This picture is vivid, but it is not what modern cosmology means by the Big Bang. The Big Bang was not an explosion from one point into empty space. It was not a blast that happened somewhere inside a larger darkness. It was the expansion of space itself from an earlier hot, dense state. The universe did not begin as material spreading through a pre-existing cosmic room. The room, if we may use that word carefully, was part of what was expanding. That changes the question of a centre completely. If the Big Bang had been an ordinary explosion, then it would make sense to ask where the explosion happened. A firework has a centre, a bomb blast has an origin point, a splash in a pond has a place where the stone went in. But cosmic expansion is not like that. It is not matter flying away from one special location. It is the stretching of distances between faraway regions of space. A useful analogy is raisin bread. Imagine dough filled with raisins. As the dough rises, the raisins move farther apart from one another. From the point of view of any raisin, the other raisins appear to be moving away. The farther raisins usually appear to move away faster, because there is more expanding dough between them. No raisin has to be the special centre of the expansion inside the dough. Each one can look around and see the others receding. The analogy is not perfect, of course. Bread has an edge. Bread sits inside an oven. Bread can be improved with butter, which is not yet a recognised principle of cosmology. But the image helps with one important idea. Expansion can make every distant point appear to recede from every other distant point without requiring one central location. Another common analogy is the surface of a balloon. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther from every other dot along the surface. A creature living only on that surface would not find a centre of expansion anywhere on the surface itself. The surface stretches everywhere. The centre of the balloon lies in a higher dimensional space outside the surface. But the creature does not need that outside space to describe the expansion happening in its own world. Again, the analogy has limits. Our universe is not literally the surface of the balloon. Space is three-dimensional, not two-dimensional rubber sheet. And standard cosmology does not require the universe to be expanding into a larger surrounding space. Still, the balloon helps loosen the mistaken idea that expansion must have a central point inside the expanding universe. This scientific picture grew from both theory and observation. In the early 20th century, Georges Lemaitre used Albert Einstein's general relativity to develop a model of an expanding universe. Lemaitre understood that if space itself were expanding, distant galaxies would appear to recede from us. Soon after, Edwin Hubble's observations gave powerful evidence that distant galaxies do tend to move away from us, and that the farther away they are, the faster they appear to recede. This relationship became known as Hubble's law. In clear-spoken terms, Hubble's law says, the recession speed of a galaxy is approximately equal to the Hubble, constant multiplied by its distance. That sounds like galaxies are simply flying away through space, but the deeper meaning is subtler. On very large scales, the recession is best understood as the result of expanding space. The distance between galaxy clusters increases because the scale of space itself changes over time. Individual galaxies can still move locally under gravity, especially inside galaxy groups and clusters, but the large-scale pattern shows cosmic expansion. This is why Earth is not at the centre of the universe, even though distant galaxies appear to recede from us in every direction. Earth is at the centre of our observable universe because observation is centred on the observer. We see outward from where we are. Light reaches us from all directions, and the limit of what we can see forms a roughly spherical region around us. But that does not mean we are at the centre of the whole cosmos. An observer in a distant galaxy would also see themselves at the centre of their own observable universe. They too would see distant galaxies receding. They too would have a cosmic horizon around them. Their visible universe would overlap with ours in some places and extend beyond ours in others. They would not be wrong. They would simply be observing from a different location. The centre belongs to the viewpoint, not necessarily to the universe. This connects to the cosmological principle, one of the guiding assumptions of modern cosmology. The cosmological principle says that, on very large scales, the universe appears broadly homogeneous and isotropic. Homogeneous means similar from place to place, when averaged over enormous distances. Isotropic means similar in every direction. This does not mean the universe is smooth in every detail. It clearly is not. There are planets, stars, galaxies, clusters of galaxies, long filaments of matter, and vast cosmic voids. The universe has structure, but when cosmologists average over scales of hundreds of millions of light years, the overall pattern appears broadly even. No direction seems to point toward a cosmic centre. No observed region clearly announces itself as the special middle of everything. The cosmic microwave background supports this picture. It fills the sky in every direction with nearly the same temperature, apart from tiny variations that became the seeds of later structure. Large galaxy surveys also show a universe that, at the biggest observed scales, looks statistically similar in all directions. So when we imagine the observable universe as a sphere around us, we must remember what that sphere means. It is not a sphere with Earth at the centre of all reality. It is the region from which light has had time to reach Earth. Its centred appearance tells us about our position as observers, not about a privileged location in the cosmos. This matters for the question of the edge. A centred visible sphere does not imply a centred total universe. The edge of what we see is not the outer rim of an explosion that began here. It is a horizon formed by light travel time, cosmic expansion, and the finite age of the transparent universe. The universe has no known centre, and without a known centre, the edge becomes less like the outside of a blast, and more like the limit of a view from one quiet place inside a much larger reality. One of the strangest facts in cosmology is that some distant galaxies can recede from us faster than light. At first, this sounds impossible. It sounds as if the universe is quietly breaking one of its own most famous rules, which would be a little rude, especially after making everyone learn it in the first place. Albert Einstein's special relativity tells us that nothing carrying information can move through space faster than light. The speed of light is a universal speed limit for local motion. But cosmic expansion has a subtle loophole. The galaxies are not necessarily moving through space faster than light. Instead, the space between us and those galaxies is expanding. That distinction is essential. Special relativity limits how fast objects can move locally through space. It does not forbid the distance between extremely far apart regions from increasing faster than light, because the space between them is stretching. Imagine two ants walking on a rubber sheet. If the sheet itself is being stretched, the distance between the ants can increase, even if neither ant is running especially quickly across the surface. Their local motion over the sheet is one thing. The stretching of the sheet itself is another. The analogy is imperfect, as all universe analogies eventually are. The universe is not literally a rubber sheet, and there is no known pair of cosmic ants taking measurements with tiny clipboards. But it helps separate two ideas that are easy to confuse: motion through space and the expansion of space. On smaller scales, such as inside the solar system, inside the Milky Way, or even inside bound groups of galaxies, gravity holds objects together strongly enough that cosmic expansion does not pull everything apart. Earth is not expanding away from your kitchen. The moon is not receding because space is stretching between every cup of tea and every biscuit. Local gravitationally bound systems behave according to their own dynamics. but on the largest cosmic scales, between distant galaxy clusters that are not gravitationally bound to one another, the expansion of space dominates. As the universe expands, the distance between those faraway regions increases. This is where recession speed enters the picture. In cosmology, the recession speed of a distant galaxy describes how quickly its distance from us increases because of cosmic expansion. According to Hubble's law, the farther away a galaxy is, the faster it appears to recede. In spoken form, Hubble's law says, the recession speed of a galaxy is approximately equal to the Hubble constant multiplied by its distance. For nearby galaxies, this recession speed is far below the speed of light, but at sufficiently enormous distances, the calculated recession speed can exceed the speed of light. This does not mean the galaxy is locally racing through space faster than a beam of light would pass beside it. It means the expanding space between us and that galaxy is increasing the distance at a rate greater than light could cross in the same cosmic coordinate system. This is not a violation of special relativity. Special relativity applies cleanly to local motion in regions of space-time small enough that the expansion of the universe can be ignored. General relativity, Einstein's later theory of gravity and space-time, is the framework used for the expanding universe as a whole. In general relativity, space and time are dynamic. Distances can change because the geometry of the universe evolves. One of the main ways astronomers know the universe is expanding is through cosmic redshift. When light travels from a distant galaxy across expanding space, its wavelength stretches along with that space. A longer wavelength means the light shifts toward the red end of the spectrum, or even beyond visible red into infrared and microwave wavelengths. This stretching is called cosmological redshift. The larger the redshift, the more the universe has expanded while the light was travelling. Early in the 20th century, Vesto Slipher measured the spectra of spiral nebulae, objects later understood to be galaxies beyond the Milky Way. He found that many of them showed redshifts, meaning their light was shifted toward longer wavelengths. These measurements became crucial evidence for the expansion picture later developed through the work of Georges Lemaitre and Edwin Hubble. Lemaitre used general relativity to describe an expanding universe, and Hubble's observations showed that more distant galaxies generally have larger redshifts. Together, theory and observation revealed that the universe was not static. It was expanding on the larger scales. This expansion also changes what we mean by the edge of what we can see. Some galaxies we observe today are so distant that, because of ongoing expansion, they are now receding from us faster than light. We can still see them because the light reaching us now was emitted long ago, when those galaxies were closer, and conditions allowed the light to make progress toward us. Over billions of years, that light crossed the expanding universe and finally arrived. But the current light being emitted by some of those same galaxies may never reach us. This is a profound idea. There are galaxies visible in our telescopes whose present-day state may already be forever beyond our future observation. We see their ancient past, but not their current moment. The universe has changed while their old light travelled, and expansion has carried them into regions from which new signals may never arrive. That deepens the meaning of cosmic horizons. The edge of the observable universe is not just a matter of what our telescopes are powerful enough to detect today. It is shaped by the finite speed of light, the age of the universe, and the expansion history of space-time. And because the expansion of the universe is accelerating, there is also a future limit, a boundary beyond which events happening now can never send light to us. So the cosmic edge is not one simple line. There is the edge of what we can currently observe. There is the edge of what has had time to reach us. And there is the edge of what will ever be able to reach us in the future. The universe is not breaking relativity by letting distant galaxies recede faster than light. It is showing us that relativity, when applied to the whole cosmos, is stranger than the simpler rule we first learn. Nothing locally outruns light, but space itself can stretch in such a way that distant regions slip beyond our reach, and beyond that growing horizon lies not merely what we have not yet seen, but some things we may never see at all. A horizon is not always a wall. Sometimes it is simply the place where information runs out. That is the key to understanding cosmic horizons. In cosmology, a horizon is not a physical border made of matter. It is not a shell, a surface, or a fence built around the visible universe by an unusually ambitious committee. It is a limit set by light travel time, cosmic expansion, and causality. Causality means the ability of one event to affect another. If light or any signal cannot travel from one region to another, then those regions cannot exchange information in the ordinary physical sense. They may both exist, but they are beyond each other's reach. This is why the word edge becomes tricky. There is more than one kind of cosmic edge, because there is more than one kind of question we can ask. We can ask what light has reached us by now. We can ask what light will ever reach us in the future. We can ask what regions can affect us. We can ask how fast distance is growing because space itself expands. Each question gives a different horizon. The particle horizon is the limit of what light could have reached us from since the early universe became transparent. It describes the boundary of the observable universe in principle, not simply what our current telescopes happen to detect, but the greatest distance from which any freely travelling light could have arrived by now. This horizon exists because the universe has a finite age, and because light travels at a finite speed. Even though the universe may extend far beyond what we see, there has not been enough cosmic time for light from every region to reach Earth. The particle horizon is therefore the edge of arrived information. It is the answer to the question, what could we have seen by now? But there is another horizon, and it is even stranger. The cosmic event horizon is the boundary beyond which events happening now may never be able to send signals to us, even if we waited forever. This horizon exists because the expansion of the universe is accelerating. Distant regions are being carried away by the growth of space so quickly that light emitted from them today may never overcome the increasing distance. This does not mean those regions have vanished. It does not mean they have hit a wall or fallen into nothing. It means their future signals cannot reach us. Their present and future are cut off from our future by the behaviour of expanding space-time. The event horizon answers a different question. What can ever affect us? That is not the same as the particle horizon. The particle horizon is about what has had time to reach us so far. The event horizon is about what can ever reach us from now onward. One looks backward through cosmic history. The other looks forward into cosmic fate. Then there is the Hubble sphere. The Hubble sphere is the distance at which recession due to cosmic expansion equals the speed of light. In simple spoken terms, it is the region where space is expanding so that a galaxy's recession speed, measured in cosmological coordinates, is equal to the speed of light. This sounds as if the Hubble sphere should be the edge of the observable universe, but it is not. Light can sometimes reach us from galaxies that were once receding faster than light, because the expansion rate changes over time, and because the path of light through expanding space is more subtle than a simple race. The Hubble sphere is useful, but it is not a solid boundary and not the same thing as the particle horizon. This is where confusion easily enters. One horizon asks what we can see now. Another asks what we will ever see. Another marks where recession speed equals light speed in a particular cosmological description. All of them are real scientific ideas, but they are not interchangeable. It is a little like using the word border for several different things. A coastline, a national boundary, A property line and the edge of a shadow can all be called borders in ordinary language, but they do not mean the same thing. One is shaped by water, one by politics, one by paperwork, and one by light. Treating them as identical would quickly lead to trouble, and possibly an argument with a surveyor. Cosmic horizons are similar. They all feel like edges, but they are edges of different kinds of knowledge. Black holes give us a useful analogy, if we use it carefully. A black hole event horizon is the boundary beyond which light cannot escape to distant observers. It is not a solid surface. An astronaut crossing a large black hole's event horizon would not necessarily hit anything at that exact boundary. The horizon is a causal boundary, a line that separates events that can send signals outward from events that cannot. Cosmic horizons are also causal boundaries, but the universe is not simply a black hole around us. The observable universe is not enclosed by a black hole event horizon in the ordinary sense. We are not sitting inside a cosmic prison with a physical shell at the edge. The analogy helps because both involve limits on signals, but it should not be stretched too far. Roger Penrose's work on causal structure made these ideas clearer. Penrose developed ways of drawing space-time diagrams that compress infinity into a manageable picture while preserving the paths light can take. These diagrams help physicists see which regions of space-time can influence one another, which signals can arrive, and where horizons form. They are not just drawings of space, they are maps of possible cause and effect. That is what horizons really reveal. They show not just where things are, but whether information can travel between them. So when we ask what lies beyond the edge of the universe, we have to ask which edge we mean. Beyond the particle horizon may be regions whose light has not reached us yet. Beyond the cosmic event horizon may be events whose signals will never reach us. Beyond the Hubble sphere may be galaxies whose distance from us is increasing faster than light in cosmological coordinates, though some of their older light can still arrive. Each version changes the answer. The universe does not give us one simple rim. It gives us layers of visibility, reachability, and causal connection. The edge is not a place where space necessarily stops. It is often a boundary between what can be known and what cannot, between what is spoken to us in light and what remains silent. Beyond the edge, then, may mean beyond what we have seen, or beyond what we will ever see, or beyond what can ever affect us. And those are not the same mystery. The shape of the universe is not only a question of what it looks like, it is a question of how space itself behaves. When we ask whether the universe has an edge, whether it continues forever, or whether it might somehow loop back on itself, we are really asking about the geometry of the cosmos, not the shapes of galaxies, nebulae, or clusters, but the deeper shape of space on the larger scales. This is where cosmology becomes beautifully strange. Space is not necessarily a rigid, empty container. In modern physics, space can have curvature. It can have geometry. It can be affected by matter, energy, and expansion. And that geometry helps determine whether the universe might be finite, infinite, closed, open, or something subtler than those ordinary words suggest. There are three broad geometric possibilities often discussed in cosmology: positive curvature, zero curvature, and negative curvature. Positive curvature is the easiest to imagine with an analogy. A two-dimensional surface with positive curvature resembles the surface of a sphere. If you draw a large triangle on a sphere, its angles can add up to more than they would on a flat sheet of paper. Lines that begin as parallel can eventually meet. A traveller moving in a straight enough path across the surface could, in principle, come back to where they began without ever finding an edge. This does not mean the universe is literally the surface of a sphere. The surface of a sphere is two-dimensional, while the space we move through has three dimensions. But the analogy helps show how a space can be finite, and still have no boundary. There need not be a cliff, wall, or final rim. Zero curvature is the familiar geometry of a flat plane. In a flat space, parallel lines remain parallel, and the angles of a triangle add up in the ordinary Euclidean way. If the universe were exactly flat and had the simplest possible topology, it could extend infinitely in every direction. That is often the simplest mental picture of a flat universe. Endless space, no edge, no loop, no final border. Negative curvature is harder to picture, but the usual two-dimensional analogy is a saddle shape. On a negatively curved surface, space spreads outward in a different way. Triangles can have angles that add up to less than in flat geometry, and initially parallel paths can diverge. In a simple version, a negatively curved universe would also be open and infinite. These analogies are useful, but they must be handled gently. Real, cosmic geometry is not a literal two-dimensional surface. The universe is not a beach ball, a sheet of paper, or a saddle sitting in some larger furniture showroom of reality. These images help us think about curvature, but the actual question concerns the geometry of three-dimensional space, described mathematically inside the framework of general relativity. Albert Einstein's general relativity made this question physical rather than merely philosophical. In general relativity, gravity is not just a force pulling objects through an unmoving background. Matter and energy influence the geometry of space-time, and that geometry influences the motion of matter and light. Space and time are dynamic parts of the universe. Einstein's field equations express this relationship. In ordinary spoken terms, they say that the geometry of space-time is connected to the distribution of matter and energy. The more matter and energy there is, and the way it is arranged, the more space-time can curve and evolve. For the whole universe, these ideas were developed further by Alexander Friedmann. In the early 20th century, Friedmann found solutions to Einstein's equations that described expanding and contracting universes. These became the basis for the Friedmann equations, which connect the expansion of the universe to its matter, radiation, curvature, and dark energy content. The Friedmann equations are central to modern cosmology, because they show that the universe's expansion is linked to what the universe contains and how space is curved. The shape of the universe is therefore not decorative. It is part of the physical story. So how do cosmologists measure curvature? One of the most powerful tools is the cosmic microwave background, the oldest freely travelling light we can observe. This ancient radiation carries a pattern of tiny temperature variations from the early universe. Those variations have characteristic sizes, and their apparent size on the sky depends on the geometry of space between us and that ancient light. If space were positively curved, the pattern would appear distorted in one way. If space were negatively curved, it would appear distorted in another. If space were flat, the pattern would have a particular expected scale. The European Space Agency's Planck satellite measured the cosmic microwave background with extraordinary precision. Its results suggest that the observable universe is very close to spatially flat, within the limits of measurement uncertainty. This means that, across the region we can observe, space behaves very nearly like flat geometry on the larger scales. That does not mean the universe is small, simple, or fully understood. It means that if there is curvature, it is either extremely slight across our observable region, or hidden on scales much larger than we can currently measure. A spatially flat universe may be infinite. That is one possible interpretation, and it fits naturally with many simple cosmological models. If space is flat and continues in the simplest way, then there may be no edge at all. The universe may simply go on and on, with more regions beyond our horizon than light can ever show us. But flatness alone does not absolutely prove infinity. This is where topology complicates the picture. Geometry tells us about curvature. Topology tells us how space is connected overall. A space can be locally flat and still have a finite global structure. For example, in simplified mathematical models, space could wrap around so that travelling far enough in one direction might eventually bring you back from the opposite direction. A flat video game map sometimes works like this. Walk off one side and you reappear on the other. The universe is not known to behave that way, and if it does, the scale would likely be far beyond anything we have detected. Also, the universe has so far failed to provide cheerful background music, which is probably wise. Still, the idea matters. Even if space has no obvious curvature, it could in principle have a more complicated global shape. Cosmologists have searched for signs of this, including repeated patterns in the cosmic microwave background. But no convincing evidence has shown that our observable universe wraps around on itself. So the shape of the universe remains partly known and partly mysterious. We know the observable universe appears extremely close to flat. We know general relativity allows different kinds of cosmic geometry. We know curvature is connected to expansion, matter, energy, and the large-scale history of the cosmos. But we do not yet know the full global shape of all space. That uncertainty matters for the question of the edge. If the universe is infinite, there is no edge. If it is finite but curved or topologically connected, it may still have no edge. If it is vastly larger than the observable universe, then any boundary or looping structure may lie far beyond what light can reveal. The shape of the universe, then, does not give us a simple rim to point toward. It gives us a deeper possibility. The cosmos may be built in such a way that an edge was never required. The shape of space is one question. The way space is connected is another. This second question belongs to cosmic topology. Topology is the study of connection, continuity, and overall structure. In cosmology, it asks whether space simply extends outward forever, whether it is finite, whether it might wrap around on itself, and whether a traveller going far enough in one direction could ever return from another. That sounds almost playful, like the universe has quietly borrowed an idea from an old video game map. Walk far enough to the right, and you appear again on the left. But behind the strange image is a serious scientific question. Does space have a global shape that is larger and subtler than anything we can directly see? To understand why this is possible, it helps to separate curvature from topology. Curvature describes the local geometry of space. It tells us whether space behaves like positive curvature, zero curvature, or negative curvature across the region we can measure. Current observations suggest that the observable universe is very close to spatially flat, but topology asks a different question. It asks how space is connected overall. A space can be locally flat and still have an unusual global connection. A simple analogy is the surface of Earth, though as always, it is limited. Earth's surface is finite. It has a definite area. Yet if you travel across it, you do not find a final border where the surface stops. There is no edge where the ground ends, and a sign politely announces, "You have completed geography." If you keep moving in a straight enough path, ignoring oceans, mountains, and the practical issue of snacks, you can eventually return to where you began. Earth's surface is finite but unbounded. The universe might, in principle, have a three-dimensional version of this idea. It could be finite in total volume without having an edge. It might not end at a wall. Instead, space could be connected in such a way that travelling far enough eventually brings you back around. One famous mathematical possibility is called a three-torus universe. A two-dimensional torus is the surface of a donut, but a three-torus is not simply an ordinary donut floating in space. It is a way three-dimensional space could be connected. In a simplified version, if you travelled far enough in one direction, you might eventually return from the opposite direction. Light could also travel around the universe, meaning that, in principle, we might see repeated images of the same cosmic structures in different directions. This does not mean the universe is known to be a three-torus. It is a speculative possibility, not an established fact. There is no evidence that astronauts could set off in one direction and eventually arrive behind themselves looking slightly tired and in need of a sandwich. But the model is useful because it shows that an edge is not the only alternative to infinity. A finite universe does not necessarily need a boundary. Cosmologists have looked for signs that space might wrap around within the region we can observe. One important place to search is the cosmic microwave background, the oldest freely travelling light in the universe. If space were finite and wrapped around, on a scale comparable to the observable universe, light from the same early regions might reach us along different paths. That could create repeated patterns in the cosmic microwave background. One possible signature would be matched circles. The idea is that if the observable universe overlapped with itself because of cosmic topology, the cosmic microwave background might contain pairs of circles with matching temperature patterns. Finding such matched circles would be a powerful hint that space is connected in a repeating way. It would suggest that the same region of the early universe was being seen from different directions. So far, searchers have not found convincing evidence for this. Measurements from cosmic microwave background missions, including NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, have been used to test these ideas. The results do not show clear repeated patterns that would prove a small wrapped universe. If space does loop back on itself, then the scale is likely larger than the observable universe, or the topology is more subtle than current searches can reveal. Researchers have explored many possible finite cosmic topologies. Jean-Pierre Luminet and collaborators, for example, investigated models such as the Poincaré dodecahedral space, a positively curved finite universe with a complex repeating structure. This was proposed as one possible way to explain certain large-scale features in the cosmic microwave background, though it has not become a confirmed description of reality. That distinction matters. Cosmic topology is not wild guesswork, but neither is it settled fact. It is a scientific attempt to ask what kinds of global structure are allowed by geometry, general relativity, and observation. Some models are elegant, some are testable in principle, some have been constrained by data. But no current observation has shown that the universe is small enough to wrap around within the observable region. This means that, as far as we can tell, looking outward does not reveal repeated copies of the same galaxies arranged like reflections in a cosmic hall of mirrors. The visible universe appears vast, nearly flat, and not obviously self-repeating. If there is a loop, it lies beyond our direct evidence. Still, the possibility changes the meaning of the title. Beyond the edge might not mean outside. In some geometries, going beyond what seems like an edge could eventually lead back around. The universe would not have an outer wall, it would not need a surrounding emptiness. It would simply be connected in a way that ordinary imagination finds difficult, because our minds evolved inside rooms, landscapes, and horizons, not inside global three-dimensional topology. So the question remains open in a careful way. Space may be infinite, space may be finite, but so large that its full structure lies beyond the observable universe. Space may have a topology that does not reveal itself within the region light has shown us. But if space does loop back, then the ultimate answer to what lies beyond the edge would be beautifully strange. Not an outside, not a wall. But perhaps, after distances too vast to measure, more of the same universe returning by another route. On the largest scales we can observe, the universe is not arranged like a smooth mist of galaxies. It has structure. Galaxies gather into groups. Groups gather into clusters. Clusters connect along long, delicate filaments stretching across hundreds of millions of light years. Between those filaments are immense voids, regions where galaxies are much more sparse. When astronomers map this structure, the universe begins to look like a vast web. Bright knots, glowing threads, broad sheets, and enormous dark spaces between them. This is called the cosmic web. It is one of the most beautiful patterns in modern cosmology, not because it was designed to be beautiful, but because gravity has been quietly sculpting matter for nearly the entire history of the universe. The cosmic web is the large-scale architecture of matter, galaxies and clusters arranged not randomly, but along a network shaped by the growth of tiny early differences. Those differences began very small. The cosmic microwave background shows that the early universe was almost but not perfectly smooth. Some regions were very slightly denser than others. The differences were tiny, only small variations in temperature and density, but gravity is patient. A region with a little more matter had a little more gravitational pull. It attracted more matter. That made it denser, which increased its pull further. Over billions of years, this slow amplification turned faint early ripples into the grand structure we see today. Matter flowed into denser regions. Gas gathered. Dark matter formed invisible scaffolding. Galaxies formed inside dark matter halos. Clusters grew where the largest concentrations gathered. Voids became emptier as matter drained toward the surrounding sheets and filaments. The result is not a universe filled evenly with galaxies, but a universe patterned like foam, lace, or a web of faintly glowing rivers. Dark matter is essential to this story. Dark matter does not emit, absorb, or reflect ordinary light in the way stars and gas do. We do not see it directly with telescopes, yet its gravitational effects are observed in galaxy rotation, gravitational lensing, galaxy cluster motion, and the growth of cosmic structure. It appears to make up much more of the matter in the universe than ordinary atoms do. In the cosmic web, dark matter acts like the hidden framework. Ordinary matter falls into the gravitational wells created by dark matter, helping galaxies and clusters form where the underlying invisible structure is densest. Without dark matter, the universe would struggle to form the structures we observe within the available cosmic time. But the particle nature of dark matter remains unknown. Scientists do not yet know whether it is made of one kind of particle, several kinds, or something even stranger. It is one of the great missing pieces in the otherwise remarkably successful picture of cosmic structure. Astronomers have mapped the cosmic web through large surveys of galaxies. The Sloan Digital Sky Survey created detailed three-dimensional maps of millions of galaxies and quasars, revealing filaments, clusters, and voids across huge volumes of space. The 2-degree field galaxy redshift survey also helped show the large-scale distribution of galaxies, strengthening the evidence for a structured but statistically uniform cosmos. The Dark Energy Survey mapped hundreds of millions of galaxies and studied cosmic structure, gravitational lensing, and the influence of dark energy on the growth of the universe. The European Space Agency's Euclid mission is designed to map the geometry and growth of cosmic structure across billions of light years, helping scientists understand dark matter, dark energy and the expansion history of the universe. These surveys do not simply give us pretty maps, although the universe has been rather generous in that department. They test the basic assumptions of cosmology. They show how matter is arranged. They reveal how structure has grown over time. They help confirm that on very large scales, the universe appears broadly similar in every direction and from place to place. This brings us back to the question of what lies beyond the observable edge. Within the region we can see, the universe looks statistically uniform on the larger scales. It is not identical everywhere, because no two galaxies or clusters are exactly the same. But when cosmologists average over enormous distances, the universe does not appear to change into something completely different in one direction. There is no observed side where galaxies suddenly thin out toward a final border. There is no evidence that we are near the edge of a cosmic island. Because of this, cosmologists infer that regions beyond our horizon may contain more of the same large-scale structure. More galaxies, more clusters, more filaments, more sheets, more voids, and more dark matter shaping them all. This inference is grounded in the cosmological principle, the idea that the universe is broadly homogeneous and isotropic on very large scales. It is supported by the cosmic microwave background and by galaxy surveys. But it is still an inference. We cannot directly check what lies beyond the horizon, because light from those regions has not reached us, and perhaps never will. That is the honest boundary. Science can say what the evidence suggests. It can extend a well-tested pattern beyond the region we can observe. It can explain why more cosmic web is the most conservative expectation. But it cannot take a photograph of something outside the observable universe. The horizon remains a horizon, and the likely answer is both comforting and astonishing. Beyond the edge we can see, there may not be an exotic wall, a glowing border, or a sudden transition into absolute nothingness. There may simply be more universe, more vastness, more hidden galaxies, more dark matter halos, more luminous threads stretching across unimaginable distances, more voids so large that entire galaxy clusters would look like small details along their edges. The universe beyond our horizon may not be stranger because it is completely different. It may be stranger because it continues. The universe we can see may be only a small piece of something far larger. That possibility comes from one of the most important ideas in modern cosmology: cosmic inflation. Inflation is the proposal that, in an extremely early moment after the Big Bang, the universe expanded at an astonishing rate. Not quickly in the ordinary sense, like an explosion racing through space, but through the rapid stretching of space itself. This inflationary phase may have happened in a tiny fraction of the first second. It would have been over almost immediately by ordinary standards, far faster than a blink, far faster than a heartbeat, far faster than the time it takes to wonder whether the universe was perhaps being a little dramatic. But in that unimaginably brief interval, space may have expanded by an enormous amount. Cosmic inflation was developed to solve several deep puzzles about the early universe. One of the most important is the horizon problem. The cosmic microwave background, the oldest light we can see, has almost the same temperature in every direction. No matter where we look in the sky, this ancient glow is remarkably uniform. There are tiny variations, and those variations matter greatly, but the overall temperature is almost identical across widely separated regions. That is surprising. Without inflation, regions on opposite sides of the observable universe would not seem to have had enough time to exchange light, heat, or information before the cosmic microwave background was released. They should not have been able to settle into nearly the same temperature. It would be like finding 2 cups of tea on opposite sides of a continent, both cooled to almost exactly the same warmth, even though they had never been in contact. A pleasing thought, perhaps, but a suspicious one. Inflation offers an answer. It suggests that the regions we now see on opposite sides of the sky were once close together before inflation occurred. They could have shared a common physical state. Then inflation stretched that once connected region to an immense size, separating parts of it so widely that they now appear far beyond ordinary causal contact. So the cosmic microwave background looks uniform because the visible universe may have come from a small patch that was already smoothed out before inflation stretched it across vast distances. Another puzzle is the flatness problem. The observable universe appears very close to spatially flat. Its large-scale geometry is not strongly positively curved or strongly negatively curved, at least within the precision of current measurements. Without some mechanism like inflation, this near flatness seems to require extremely finely balanced early conditions. Inflation helps because rapid expansion stretches space. Just as inflating a tiny part of a balloon makes that patch look flatter and flatter to a small observer living on it, cosmic inflation could stretch any initial curvature until the observable region appears almost flat. The whole universe might still have a more complicated global shape, but our visible patch would look very close to flat. A third puzzle concerns magnetic monopoles. Some grand unified theories in particle physics predicted heavy particles with a single magnetic pole, either north or south, rather than the north and south pair found in ordinary magnets. These magnetic monopoles have not been observed. Inflation could explain their absence by diluting any such particles to incredibly low densities, spreading them so far apart that none would be expected within our observable universe. The idea of inflation was developed by several major figures. Alan Guth proposed an influential version of inflation in the early 1980s. Alexei Starobinsky had earlier developed an inflation-like model in the context of quantum corrections to gravity. Andrei Lindy developed important versions, including chaotic inflation. Paul Steinhardt also contributed significantly to early inflationary theory and later became one of its thoughtful critics, which is useful because science works best when even elegant ideas are not allowed to sit too comfortably in the armchair. Inflation is not just an imaginative addition to cosmology. It has broad observational successes. It helps explain why the observable universe is so uniform on large scales. It helps explain why space appears so close to flat. It also predicts a pattern of primordial fluctuations, tiny variations in density that could later grow into galaxies and the cosmic web. Observations of the cosmic microwave background by missions such as NASA's Wilkinson Microwave, Anisotropy Probe, and the European Space Agency's Planck satellite are broadly consistent with this inflationary picture. Those fluctuations are crucial. In inflationary models, quantum fluctuations in the very early universe are stretched to cosmic scales. After inflation ends, these tiny differences become the seeds of later structure. Gravity gradually amplifies them over billions of years, forming stars, galaxies, galaxy clusters, filaments, and voids. In this sense, inflation connects the very smallest scales of early physics with the larger structures in the modern universe. A tiny ripple in the early cosmos can become part of the pattern that eventually shapes a galaxy cluster. It is one of those ideas that sounds almost too strange to be allowed, but the universe has never shown much interest in being modest. Still, the exact inflationary model remains uncertain. Cosmologists do not yet know precisely what physical field drove inflation, how inflation began, how it ended, or which version, if any, is the final correct description. Inflation is a powerful framework, strongly supported by several broad lines of evidence, but not a single completed theory with every detail settled. There are many models of inflation, and observations continue to narrow them down. This uncertainty matters because inflation changes the meaning of the edge of the universe. If inflation happened, then the observable universe may be only a tiny patch of a vastly larger region produced by the same early expansion. The space beyond our horizon may not merely be a little farther than we can see. It may extend for distances so enormous that our observable universe is like a small lit window in a building whose full size we cannot measure. Beyond the edge of the observable universe, there may be more space created by the same inflationary stretching. More regions with galaxies, more cosmic web, more patches of matter and radiation that began from the same early process, but are forever beyond our view. In some versions, inflation may lead to an even stranger possibility called eternal inflation, where inflation ends in some regions but continues elsewhere, potentially producing separate bubble universes. That idea is more speculative. It belongs to the open frontier of theoretical cosmology, not to the same level of confidence as cosmic expansion, the cosmic microwave background, or the basic success of the inflationary framework. So the careful answer is layered. Inflation gives us strong reasons to think the universe may be far larger than the observable region. It may explain why the visible universe is smooth, flat and structured in the particular way we see, but the most exotic extensions, such as eternal inflation and bubble universes, remain uncertain and difficult to test. Even so, inflation leaves us with a profound possibility. The edge we see may not be close to the edge of all there is. It may be only the edge of one observable patch, stretched from an ancient beginning, surrounded by more universe than light will ever be able to show us. There is a version of the universe in which our observable cosmos is not the whole story, but one settled region inside a much larger, still expanding reality. This idea is called eternal inflation. It begins with cosmic inflation, the proposal that the very early universe underwent a period of extremely rapid expansion. In the usual picture, inflation ended in our region, energy transformed into particles and radiation, and the universe continued expanding more slowly, allowing matter, atoms, stars, and galaxies to form. Eternal inflation takes that idea further. It suggests that inflation may not have ended everywhere at once. In some regions, inflation stops. In other regions, it continues. Where it stops, a universe like ours can begin its more familiar history, cooling from a hot, dense state, forming particles, atoms, galaxies, stars, and eventually the kind of cosmic web we observe. But elsewhere, inflation keeps driving space apart at an extraordinary rate. The result could be a vast inflating background in which many separate regions form, each one like a bubble where inflation has ended. These are often called bubble universes. The phrase is vivid, but it needs careful handling. A bubble universe is not necessarily a shiny sphere floating next to ours in a larger empty room. It is not a neighbouring place just beyond the visible edge, waiting for a sufficiently determined spacecraft with excellent fuel economy. It would be a region of space-time with its own cosmic history, likely separated from us by the continuing expansion of space. In this picture, our observable universe would lie inside one such region. Inflation ended here, or at least in the larger region that contains everything we can observe. That ending allowed the energy driving inflation to become the hot mixture of particles and radiation from which the later universe developed. Over time, the universe cooled, atomic nuclei formed, atoms formed, light began to travel freely, gravity built stars and galaxies. In other bubble universes, if they exist, the details might be different. Some models suggest that different bubbles could have different histories. They might begin with different conditions. They might expand differently. In more speculative versions, they might even have different physical constants, such as different particle masses or different strengths of forces. That would mean the rules shaping atoms, stars, and galaxies could vary from one bubble to another. This is an astonishing possibility, but it is not an observed fact. No telescope has seen another bubble universe. No spacecraft has crossed into one. No experiment has confirmed that such regions exist. Eternal inflation is a theoretical extension of inflation, not a settled description of reality. It belongs to the frontier where mathematics, cosmology, and speculation meet, and where everyone should walk calmly, preferably without waving a flag saying "confirmed" before the evidence arrives. Several major physicists helped develop these ideas. Andre Linde's work on chaotic inflation showed how inflation could arise in broad classes of early universe models, and how some versions could naturally lead to eternal inflation. Alexander Vilenkin also made important contributions to eternal inflation, and the idea that inflating space-time could continually produce new regions where inflation ends. Their work helped turn the multiverse from a loose philosophical image into a serious, if still speculative, topic in theoretical cosmology. The central mechanism is subtle. Inflation expands space extremely quickly. If quantum effects cause inflation to stop in one region, that region can form a bubble where ordinary cosmic evolution begins. But if surrounding regions keep inflating, then the total inflating space can grow faster than bubbles form and settle. This means inflation may continue forever into the future in some parts of the larger space-time, producing more and more bubble regions. From inside one bubble, observers would not see the larger process directly. They would see their own observable universe. They would see galaxies, cosmic microwave background radiation, expansion, dark matter, dark energy, and all the local evidence available within their horizon. The other bubbles, if they exist, would likely be far beyond causal contact. Their light would not reach us. Their events would not influence us in any ordinary way. This is why bubble universes are not simply places beyond a wall. They are not hidden behind the cosmic microwave background like another room behind a curtain. They would be separated by the structure and expansion of space-time itself. Reaching one would not be like travelling past the last galaxy and turning left. The problem is not distance alone, it is causality. Testing eternal inflation is therefore extremely difficult. One possible idea is that if two bubble universes collided in the early stages of their history, the collision might leave a faint imprint in the cosmic microwave background. Scientists have searched for unusual circular patterns or asymmetries that could, in principle, hint at such an event. But no evidence has been widely accepted as a confirmed bubble collision. Possible signs remain uncertain, controversial, and very difficult to separate from statistical flukes, foreground effects, or ordinary features of cosmic structure. This difficulty creates a serious scientific challenge. A theory becomes stronger when it makes clear predictions that can be tested. Inflation itself has broad observational support because it helps explain the near uniformity of the cosmic microwave background, the near flatness of the observable universe, and the pattern of primordial fluctuations. Eternal inflation is harder, because much of what it predicts may lie permanently beyond our horizon. That does not make it meaningless, but it does mean we must keep the confidence level clear. Cosmic expansion is well established. The cosmic microwave background is directly observed. The basic idea that inflation may have occurred is strongly motivated and broadly successful. Eternal inflation and bubble universes are more speculative. They may be true, they may be incomplete, they may be pointing towards something deeper that future physics will describe in a different way. This is where the question of the edge enters its most uncertain territory. Beyond our cosmic horizon, there may simply be more of our universe, more galaxies, more filaments, more voids, more regions shaped by the same early conditions. That is the conservative expectation. But in some inflationary models, beyond what we can ever observe, there may also be other regions where inflation ended differently, forever separated from us by expanding space-time. Not beyond an edge we could approach, but beyond a causal boundary that may be absolute. So the answer becomes layered. Beyond the edge we see may be more universe. Beyond what we can ever see may be more of the same. And beyond the reach of direct evidence, in the speculative landscapes of eternal inflation, there may be other cosmic bubbles with histories of their own. Not confirmed, not reachable, but possible enough to remind us that the observable universe may be only one quiet clearing in a far larger inflationary wilderness. Dark energy is the name we give to one of the strangest facts about the universe. The expansion of space is not slowing down as much as astronomers once expected. On the larger scales, it is accelerating. Distant galaxies are not only receding from one another because space expands. Over cosmic time, that expansion appears to be speeding up. This was not the result most scientists expected. For much of the 20th century, the natural question was whether gravity would slow the expansion of the universe. Matter attracts matter. Galaxies, clusters, gas, dark matter, and radiation all contribute to gravity. So it seemed reasonable to ask whether the universe contained enough mass to eventually halt expansion, perhaps even reverse it, or whether it would simply expand forever at an ever slower rate. Then observations of distant exploding stars changed the story. In the late 1990s, two research groups studied Type Ia supernovae, powerful stellar explosions that can be used as cosmic distance indicators. Type Ia supernovae are useful because their intrinsic brightness can be standardized. By comparing how bright they truly are expected to be with how faint they appear from Earth, astronomers can estimate their distances. The two groups were the Supernova Cosmology Project and the High Z Supernova Search Team. The Supernova Cosmology Project was led by Saul Perlmutter. The High Z Supernova Search Team included key figures such as Brian Schmidt and Adam Rees. These teams examined distant Type Ia supernovae to measure how the expansion of the universe had changed over time. The result was startling. The supernovae appeared dimmer than expected in a universe whose expansion was slowing under gravity alone. The best explanation was that the expansion of the universe had once been slowing, but had later begun to accelerate. Something was causing space to expand faster over time on the larger scales. That something became known as dark energy. The name is honest in its own quiet way. Dark energy does not mean scientists fully understand what it is. It means there appears to be a component of the universe, or a property of space-time itself, that drives accelerated expansion. It is called dark because it is not seen directly as ordinary light. It is called energy because in the equations of cosmology, it behaves as a form of energy associated with the expansion of space. The simplest model of dark energy is the cosmological constant. Albert Einstein originally introduced the cosmological constant into his equations of general relativity as a way to allow a static universe. At the time, before the expansion of the universe was established, many scientists assumed the cosmos was eternal and unchanging on the larger scales. Einstein later moved away from that idea after evidence for expansion grew stronger. But the cosmological constant returned in modern cosmology with a very different role. Today, it is used as the simplest explanation for dark energy. In this view, empty space itself has a constant energy density. As space expands, more space exists, and this constant energy of space drives accelerated expansion. It is not a wind pushing galaxies through space. It is a property of the expanding geometry of the universe. This has a deep effect on cosmic horizons. If the expansion of the universe was slowing in a simple way, More and more distant light might gradually reach us over time. The observable universe would continue changing, and ancient signals from farther regions could arrive. But accelerated expansion creates a future limit. Some regions are being carried away so quickly by the growth of space that light emitted from them now will never reach us. This boundary is called the cosmic event horizon. As expansion accelerates, more galaxies will eventually cross beyond our cosmic event horizon. This does not mean they suddenly vanish in their own local surroundings. It does not mean they are destroyed, frozen, or swallowed by an actual wall. Their stars may continue shining. Their planets, if they have any, may continue orbiting. Their local physics remains ordinary. But from our perspective, their future light will never arrive. The expanding geometry of space-time prevents future signals from crossing the growing distance. We may still see ancient light from some galaxies for a very long time, increasingly redshifted and faded, but their present and future become inaccessible. They slip beyond possible communication, not because they stop existing, but because the universe's expansion changes what can ever be known. This gives the edge of the universe a new meaning. The edge is not fixed. The boundary of what can communicate with us changes with cosmic history. There is the edge of what we can see now, shaped by the age of the universe and the travel time of light. There is also the edge of what we will ever be able to see, shaped by accelerated expansion and dark energy. In the very distant future, the universe may look much lonelier to any observers who remain. Our galaxy, the Milky Way, is gravitationally bound to the local group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and many smaller galaxies. Over billions of years, the Milky Way and Andromeda are expected to merge into a larger galaxy. The local group as a whole will remain bound by gravity. But galaxies beyond the local group, and beyond other gravitationally bound structures, will continue to be carried away by cosmic expansion. As dark energy drives acceleration, distant galaxies will become more redshifted, fainter, and eventually unreachable in light. The wider universe will not disappear all at once. It will fade from contact. Future astronomers, if they exist in the far future, may see a dark sky dominated by their own merged galaxy and its local companions. The evidence for cosmic expansion could become far harder to recover. The cosmic microwave background will be stretched to wavelengths so long and faint that detecting it may be extremely difficult. Most external galaxies will lie beyond observational reach. The universe will not have ended. But the visible universe will have shrunk in a meaningful sense. Not because space has become smaller, but because the number of regions able to send us new information will have diminished. That is the quiet power of dark energy. It turns the edge of the universe from a simple question about distance into a question about time, fate, and communication. What we can see is not only limited by where light has come from, it is also limited by where light can ever come from. The cosmic horizon is not a permanent fence drawn once and for all. It is part of the evolving universe. And because the expansion of space is accelerating, some of what is visible now will one day become unreachable. The universe beyond the edge may still exist, filled with galaxies and structure, but its future may be sealed away from ours. The edge is not a wall of matter. It is a changing boundary of contact. And dark energy is slowly moving that boundary farther into silence. If the universe is expanding, what is it expanding into? It is one of the most natural questions in all of cosmology. It feels almost unavoidable. If something grows, surely it grows into something. A balloon expands into the air around it. A cloud expands into the sky. A ripple expands across water. A crowd expands into an available room. Usually just when everyone decides they also need to be near the snacks. So if the universe is expanding, the mind reaches for the same pattern. It imagines space swelling outward into a larger emptiness. It imagines the cosmos as a bubble, with galaxies on the inside and some wider darkness on the outside. And then the question follows, what is outside the bubble? But in standard cosmology, the expansion of the universe does not require an external container. Expansion means that distances between widely separated points in space increase over time. It does not necessarily mean that the universe is moving into a surrounding region. The universe is not like gas spreading through a box, where the box already exists and the gas fills more of it. In the cosmological picture described by general relativity, space itself is part of what evolves. This is difficult because every ordinary example of expansion takes place inside space. Bread rises in an oven, a balloon inflates in a room, a wave spreads across a surface. Our intuition is trained by things that are already located somewhere. But the universe is not merely located within space. In the broadest physical meaning, the universe includes space. That is why the question can become slippery. When cosmologists say the universe is expanding, they mean that the scale of space is changing. Distant galaxy clusters become farther apart because the geometry between them evolves. The expansion is not measured by looking for a center or an outer boundary. It is measured through effects such as cosmic redshift, where light from distant galaxies is stretched to longer wavelengths as space expands during the light's journey. The balloon analogy can help, but only for a moment. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart along the surface. From the point of view of a tiny creature living only on that surface, every distant dot appears to recede. There is no center of expansion on the surface itself. Expansion happens everywhere on the surface. That part is useful. But the analogy can also mislead, because the balloon expands into surrounding air. It has an inside and an outside. It sits in a room. The universe, as described by standard general relativity, does not need to sit inside a larger room in order for its internal distances to grow. The surrounding air in the analogy is not meant to represent a real cosmic outside. This brings us to an important distinction: intrinsic geometry and extrinsic embedding. Intrinsic geometry is the geometry that can be measured from within a space. A traveller on Earth's surface can measure distances, angles, curvature, and routes without needing to step outside Earth and look at it from space. They can discover that the surface is curved through measurements made on the surface itself. Extrinsic embedding is the idea of placing a space inside a higher dimensional surrounding space. We often picture Earth's surface as curved because we can imagine it embedded in three-dimensional space. But the mathematics of curvature does not always require that external viewpoint. A space can have measurable geometry from within without needing a physical outside, where someone stands and looks at it. This idea became possible through the development of non-Euclidean geometry. Bernard Riemann was one of the key figures who showed that geometry could be much richer than the flat geometry of Euclid. Riemann's mathematical ideas allowed spaces to have curvature described from within. Decades later, this helped make Albert Einstein's general relativity possible, because general relativity describes gravity as the curvature of space-time, rather than as a simple force acting across a fixed background. So when we ask what is outside space, we may be asking for an external viewpoint that physics does not require. If the universe means all of space-time, matter, energy, radiation, dark matter, dark energy, and physical law, then outside the universe may not refer to a place. A place is already a location in space. A time is already part of space-time. If all of space-time belongs to the universe, then asking for a location outside it may be like asking for a place on Earth that is farther north than the North Pole. The phrase sounds meaningful because the words are familiar, but the idea may not apply. This does not mean scientists know everything. It does not mean every question about larger reality is closed. It means that we must separate a scientific unknown from a physically misplaced question. A scientific unknown is something we do not yet know, but can meaningfully investigate, such as the exact nature of dark matter, the detailed physics of inflation, or the global topology of the universe. A misplaced question is one that assumes a framework that may not exist, like asking what colour gravity is on a Tuesday. The phrase outside space may fall into that second category, at least within standard cosmology. Still, some speculative theories do introduce larger frameworks. Certain versions of string theory, M theory, and brane cosmology propose extra spatial dimensions or higher dimensional settings in which our familiar universe might be part of a larger structure. In some models, ordinary matter and light could be confined to a three-dimensional brane, while gravity interacts with additional dimensions. These ideas are mathematically serious, but they are not required by the standard cosmological model, and they are not confirmed descriptions of reality. So the safest answer is careful. The universe may not be expanding into anything. Space itself may be expanding, with distances changing from within. There may be no physical outside in the ordinary sense, and if there is some deeper framework beyond familiar space-time, it is not something established by the evidence that currently supports cosmic expansion, the cosmic microwave background, and general relativity. The question remains powerful because it exposes the limits of ordinary imagination. We are creatures of rooms, roads, maps, surfaces, and horizons. We expect things to have outsides because almost everything around us does. But the universe may not be one object sitting among others. It may be the whole stage on which the idea of outside normally depends. So when we ask what lies outside space, the answer may not be a hidden place beyond the edge. It may be that space has no outside of the kind our language is reaching for. There is another way to ask what lies beyond the universe, and it does not mean travelling farther through ordinary space. It means asking whether the space we know is only part of a deeper structure. This idea appears in extra-dimensional theories. These are speculative frameworks in which our observable universe might be connected to, or contained within, a larger reality with more dimensions than the 3 dimensions of space we experience directly. In some versions, our universe is described as a brane. A brane is a generalization of the word membrane. In physics, it can mean an extended object with a certain number of dimensions. A point has no spatial extent. A line has 1 dimension. A sheet has 2 dimensions. The familiar space around us has 3 spatial dimensions. A brane could, in principle, be a 3-dimensional spatial structure existing within a higher dimensional setting. This higher dimensional setting is sometimes called the bulk. In brane cosmology, the basic idea is that ordinary matter and light may be confined to our 3-dimensional spatial brane. That would mean atoms, stars, planets, galaxies, and photons all remain within the familiar dimensions of space. We would not see or move freely into the extra dimensions, just as a creature confined to a surface would not easily step away from that surface into a larger surrounding space. Gravity, however, may behave differently in some models. Certain brane world theories suggest that gravity could interact with additional dimensions. This is important because gravity is already much weaker than the other fundamental forces at ordinary particle scales. Some theorists have explored whether extra dimensions could help explain that weakness, or change how gravity behaves across tiny distances or extremely high energies. Lisa Randall and Raman Sundram developed influential brane world models in which our universe is represented as a brane inside a higher dimensional space-time. Their work showed that extra dimensions do not always have to be large and obvious. They can be curved, hidden, or shaped in ways that affect physics without appearing as an extra direction someone could simply point toward. That last point is important. Extra dimensions are not the same as a region beyond the visible edge of the universe. They are not like another country on the far side of the cosmic horizon. They are not just past the last galaxy, waiting beside a sign that says, "Additional dimensions, please keep left." If extra dimensions exist, they would be additional degrees of spatial structure, not necessarily distant places in the ordinary sense. This is where language can mislead us again. When we hear beyond, we usually imagine distance, something beyond the mountain, beyond the ocean, beyond the end of the road. But in extra-dimensional theories, beyond may not mean farther away through the same kind of space. It may mean deeper in the structure of space-time itself. String theory is one framework where extra dimensions often appear. In string theory, the most basic ingredients of nature are not point-like particles, but tiny vibrating strings. Different patterns of vibration correspond to different particles. To be mathematically consistent, many versions of string theory require more spatial dimensions than the familiar 3. M-theory, a broader theoretical framework related to string theory, also includes higher dimensional objects such as brains. In these ideas, our universe might be one brain among a richer set of structures in a higher dimensional reality. This is fascinating, but it remains theoretical. String theory and M-theory have not yet produced confirmed experimental evidence showing that extra dimensions physically exist. Scientists have looked for signs. One kind of search tests gravity at very small scales. Newtonian gravity works extremely well across everyday and astronomical distances, but if extra dimensions exist, gravity might deviate from the expected inverse square behaviour at tiny distances. Experiments have therefore measured gravity on very small scales to see whether it weakens or strengthens in unexpected ways. So far, no confirmed deviation has revealed extra dimensions. Another kind of search happens at high-energy particle colliders. CERN's Large Hadron Collider has looked for possible signatures that might be connected to extra dimensions, such as missing energy patterns, unusual particle production, or effects that could hint at gravity leaking into hidden dimensions. These searches are technically difficult, and many proposed signs depend on the details of a particular model. No confirmed evidence has shown that our universe is a brain inside a higher dimensional bulk. That is the careful statement. Not that the idea has been disproven in every possible form. Not that theorists invented it casually over lunch and then wandered off. The mathematics is serious, and the models have influenced cosmology, particle physics, and attempts to connect gravity with quantum theory. But evidence matters, and at present, brain world scenarios remain speculative. Still, they are useful because they expand the meaning of the question. If someone asks what lies beyond the edge of the universe, the standard answer begins with the observable horizon. Beyond what we can see may simply be more universe. But extra-dimensional theories suggest another possible sense of beyond. Not beyond the farthest light, not beyond the cosmic microwave background, not beyond the last visible galaxy. Beyond, in this case, would mean outside the familiar dimensional structure of our space-time. That possibility is very different from an ordinary edge. If our universe were part of a brain, then the larger reality would not necessarily be visible as a dark region surrounding the sky. It would not be something reached by travelling far enough in a spaceship. It would be more like discovering that the stage on which everything happens has hidden directions built into it. For now, this remains an open and speculative part of theoretical physics. The universe described by standard cosmology does not require a higher dimensional bulk. Cosmic expansion, the cosmic microwave background, galaxy formation, dark matter, and dark energy can all be studied without assuming that our universe is a brain. The standard model of cosmology works remarkably well across many observations, even though it leaves deep mysteries unsolved. But brains and extra dimensions remind us that the word beyond can point in more than one direction. It may point outward past the edge of observation, or it may point inward toward the hidden structure of space itself. And sometimes the deepest beyond is not farther away at all. It is underneath the familiar shape of reality, waiting not at the end of space, but beside the question of what space really is. An edge does not have to be a place. It can also be a moment. So far, the edge of the universe has mostly meant a spatial edge, a boundary in distance, visibility, or causal reach. But there is another kind of edge that may be even more mysterious. An edge in time, a beginning, a first moment, a point before which the usual language of physics becomes uncertain. This is where cosmology turns toward quantum cosmology. The Big Bang model tells us that the universe was once much hotter, denser, and smoother than it is today. As we run the expansion of the universe backward in our equations, galaxies move closer together, radiation becomes hotter, matter becomes more compressed, and the observable universe approaches an extremely dense early state. General relativity describes this backwards journey with remarkable power. It connects the expansion of space to the matter and energy inside the universe. It explains why the cosmos evolves rather than simply sitting still. But if we keep following general relativity backward without modification, it appears to point toward a singularity, a state where density and curvature become infinite. That is not usually treated as a normal physical place or moment. In physics, infinities often signal that a theory has been pushed beyond the range where it can safely be used. General relativity is extraordinarily successful for planets, stars, galaxies, black holes, gravitational waves, and the expanding universe. But near the earliest moments of cosmic history, the universe would have been so small, hot, and dense that quantum effects should become unavoidable. This is the problem of quantum gravity. Quantum theory describes matter, energy, particles, and fields on tiny scales. General relativity describes gravity as the curvature of space-time. Each theory works beautifully in its own domain, but the very early universe demands both at once. It asks for a theory in which space-time itself may have quantum behaviour. That is why physicists often speak of the Planck era. The Planck time is an extremely tiny interval, roughly the timescale below which our current theories stop giving confident answers about the universe's earlier state. It is about 1/10,000,000 trillion trillionth of a second. Although saying that out loud is a good way to make even time seem slightly exhausted. It is named after Max Planck, whose work helped begin quantum theory. The Planck time is often described as the earliest meaningful timescale in known physics, but it should not be mistaken for a proven first instant. It is not a confirmed wall at the beginning of time. It is a warning sign that ordinary physics is no longer enough. Before or around that scale, quantum gravity should matter, but we do not yet have a fully tested theory of quantum gravity. Stephen Hawking and Roger Penrose showed, through singularity theorems, that under broad conditions, general relativity leads to singularities and gravitational collapse in cosmic history. These theorems were profound because they showed that singularities were not merely mathematical accidents in special models. They seemed deeply connected to the structure of general relativity itself. But they also pointed toward the need for deeper physics. If general relativity predicts its own breakdown at an extreme boundary, then the singularity may not be the final answer. It may be the edge of the theory. Stephen Hawking later worked with James Hartle on the no-boundary proposal, a speculative model in quantum cosmology. In the Hartle-Hawking no-boundary proposal, the universe may not have a sharp beginning in ordinary time. Instead, the earliest universe could be described in a way where time behaves more like a spatial dimension near the beginning, smoothing out the idea of a first instant. A common analogy is the surface of Earth again. The North Pole is not an edge of Earth's surface, even though it is a special point in the coordinate system. You cannot go farther north than the North Pole, but you do not fall off the planet when you get there. Similarly, in the no-boundary proposal, the beginning of the universe might not be a hard temporal edge. It might be more like a smooth limit where the ordinary idea of before loses its usual meaning. This idea is elegant, but it is not confirmed. Other approaches give different possibilities. Loop quantum cosmology, connected with the work of Abhay Ashtekar and others, applies ideas from loop quantum gravity to the universe as a whole. In some loop quantum cosmology models, the Big Bang singularity is replaced by a bounce. Instead of beginning from an infinite density point, the universe may have emerged from a previous contracting phase that reached an extreme but finite density before expanding again. These bounce models are fascinating because they suggest that the Big Bang might not have been the absolute beginning. It might have been a transition. A previous universe or previous phase of the same universe could have contracted before rebounding into expansion. But again, this remains unconfirmed. There are many speculative ideas about what happened near the beginning. No-boundary models, bounce cosmologies, string cosmology, ekpyrotic scenarios, and other attempts to bring quantum theory and gravity together. They do not all agree. Some remove the sharp beginning, some transform it, some replace it with a deeper phase whose physics is not yet fully understood. So when we ask what lies before the Big Bang, we face a question strangely similar to asking what lies beyond the edge of space. The problem may not be lack of imagination. Human imagination is very good at inventing before and beyond. The problem is that our tested physics may not yet reach far enough. The words before the Big Bang might refer to a real earlier phase, or they might fail because time itself, as we understand it, emerged from the same early conditions. The honest answer is not simply yes or no. The edge may be an edge of observation, like the cosmic microwave background. It may be an edge of causality, like a cosmic horizon. It may be an edge of geometry, if the universe has a global structure we cannot measure. And near the beginning of time it may be an edge of theory. Beyond that edge there may be deeper physics. But for now, the beginning of the universe remains not a wall we have reached, but a frontier where our best ideas become incomplete. The word multiverse sounds as though it describes one clear idea. It does not. It is an umbrella term, and under that umbrella are several very different possibilities. Some are extensions of ordinary cosmology. Some come from inflation. Some come from quantum mechanics. Some come from string theory. They are often grouped together because they all suggest that our observable universe may not be the whole of reality, but they do not all mean the same thing. This matters because when people ask whether there are other universes, they may be asking several different questions at once. One version is the simplest. There may be regions beyond our observable universe that are still part of the same space-time. These would not be separate universes in the dramatic sense. They would simply be more universe beyond our horizon, more space, more matter, more galaxies, more cosmic web, all too far away for their light to have reached us. In that case, other universes may really mean other unobservable regions of this universe. That is the most conservative idea. It does not require entirely new laws of physics. It follows naturally from the possibility that the total universe is much larger than the observable universe, perhaps even infinite. A second version comes from inflation. In some models of eternal inflation, inflation ends in some regions but continues in others. Each region where inflation ends could become a bubble universe, with its own hot beginning, its own expansion history, and its own formation of particles, atoms, stars, and galaxies. Our observable universe would lie inside one such bubble. These bubble universes would not be neighbouring places just beyond a visible wall. They would probably be causally separated by expanding space-time. A spaceship could not simply travel beyond the last galaxy, cross a border, and arrive in another universe, hopefully after finding parking. The separation would be built into the structure of space-time itself. A third version comes from quantum mechanics. The many-worlds interpretation was proposed by Hugh Everett in the 20th century. It is an interpretation of quantum theory in which all possible outcomes of quantum events occur, but in different branches of reality. In this view, the universe does not choose one outcome while the others vanish. Instead, the total quantum state continues, with different branches corresponding to different observed results. This is very different from distant cosmic regions beyond our horizon. Many worlds is not about galaxies far away in ordinary space. It is not about bubble universes formed by inflation. It is about the meaning of quantum measurement and the structure of the quantum state. Calling it a multiverse can be useful, but only if we remember that it belongs to a different kind of question. A fourth version comes from string theory. String theory is a theoretical framework in which the fundamental ingredients of nature are tiny vibrating strings, rather than point-like particles. Many versions of string theory allow a huge number of possible vacuum states. A vacuum state in this context means possible lowest energy configuration of fields and extra dimensions. Different vacuum states could lead to different low-energy physical laws, such as different particle properties or different strengths of fundamental forces. This collection of possibilities is often called the string landscape. In some speculative pictures, different regions of a larger reality could realize different parts of this landscape. One region might have physical constants like ours, allowing atoms, stars, chemistry, and life. Another might have different constants, producing a universe with no stable atoms, no familiar stars, or physics so different that ordinary imagination quickly runs out of furniture. But this remains speculative. The string landscape is not a map astronomers have observed. It is a theoretical idea arising from attempts to connect quantum physics, gravity, and higher dimensional geometry. It may point towards something real, or it may reflect the limits of current theory. It is not established cosmic architecture. This is why the multiverse is scientifically controversial. Science depends on evidence, prediction, and testing. Some multiverse ideas may be difficult to test directly, because the other regions, bubbles, or branches are beyond communication with us. If a theory predicts things that can never affect what we observe, then scientists must ask how the theory can be evaluated. Does it explain data better than alternatives? Does it make indirect predictions? Does it arise naturally from a theory that is testable in other ways? These are serious questions, not just cautious footnotes. A multiverse can be an elegant consequence of a theory, but elegance is not enough. The universe has no obligation to reward our most dramatic ideas, even when they make excellent documentary titles. Mystery is not permission to believe anything. It is an invitation to ask better questions and to keep track of what is known, what is inferred, and what is only possible. The physicist Max Tegmark has offered a useful classification of multiverse levels. In his scheme, one level refers to regions beyond our observable universe in the same larger space. Another relates to different bubble universes from inflation. Another concerns many worlds quantum branching. Another involves deeper mathematical structures. This classification is helpful because it separates ideas that are often mixed together, but it should not be treated as confirmed architecture. It is an organizing scheme, not a telescope image. So are there other universes? The careful answer depends on what we mean. If we mean regions beyond our observable horizon, then there may very well be more universe beyond what we can see. That is a conservative possibility. If we mean inflationary bubble universes, the idea is serious but speculative. If we mean many worlds branches, we're talking about an interpretation of quantum mechanics, not distant places in space. If we mean the string landscape, we're deep in theoretical territory where evidence is still limited. This connects directly to the question of the edge. Beyond the edge might mean beyond the observable region. It might mean beyond our inflationary bubble. It might mean beyond one branch of quantum reality. Or it might mean beyond the particular physical laws realized in our part of a larger theoretical landscape. Each meaning is different. The wonder is real, but the caution is just as important. The universe may be far larger, stranger, and more layered than the part we observe. But good science does not fill the dark with certainty before the light arrives. Beyond the edge, there may be more universe. There may be other cosmic regions. There may be deeper structures of reality. But for now, the multiverse remains not a single answer, but a family of possibilities gathered around the limits of what we can know. Cosmology is not built from one kind of knowledge. Some things are directly observed. Some things are inferred from their effects. Some things are described by mathematical models that connect many observations into one picture. And some things remain speculative, meaning they may be possible, even serious, but are not yet confirmed by evidence. That distinction matters deeply when we ask what lies beyond the edge of the universe. Direct observation means receiving information from the universe itself. Light from a galaxy reaches a telescope. Microwave radiation from the early universe reaches a detector. A supernova appears in the sky and its brightness can be measured. These observations are not guesses, they are signals arriving from the cosmos. The cosmic microwave background is one of the strongest examples. It is ancient radiation released when the universe became transparent, roughly 380,000 years after the Big Bang. It has been measured across the sky with extraordinary precision, especially by the Planck collaboration, using the European Space Agency's Planck satellite. Its temperature pattern gives direct evidence about the early universe, its density variations, and its large-scale geometry. Galaxy redshift surveys provide another anchor. By measuring how light from galaxies is shifted toward longer wavelengths, astronomers can estimate how fast those galaxies recede and how far away they are. Surveys such as the Sloan Digital Sky Survey have mapped enormous numbers of galaxies, revealing the large-scale cosmic web of clusters, filaments, sheets, and voids. The Dark Energy Spectroscopic Instrument continues this work by measuring galaxy redshifts across vast regions of the sky, helping scientists trace how cosmic expansion and structure growth have changed over time. The Vera-C-Rubin Observatory is expected to add another powerful view by repeatedly imaging the sky, measuring changing objects, weak gravitational lensing, and the distribution of galaxies across cosmic time. Indirect inference is different, but still very strong when many lines of evidence agree. Dark matter is a good example. We do not see dark matter shining like stars or glowing gas, but we infer its presence from gravity. Galaxies rotate in ways that imply more mass than visible matter provides. Galaxy clusters behave as if they contain unseen mass. Gravitational lensing, where mass bends the path of light, reveals extra gravity even where little ordinary matter is visible. The growth of the cosmic web also fits a universe where dark matter provides much of the gravitational scaffolding. Gravitational lensing is especially useful because it allows astronomers to map mass, not just light. When a massive object lies between us and a more distant galaxy, its gravity bends and distorts the background light. This effect was predicted by general relativity and has become a major tool in modern cosmology. It shows where matter is, including matter that does not shine. Baryon acoustic oscillations give another kind of evidence. These are ancient sound wave-like patterns from the early universe, preserved in the later distribution of galaxies. In the young hot plasma, ordinary matter and radiation interacted in waves of compression and rarefaction. After the universe cooled and atoms formed, those patterns became frozen into the large-scale arrangement of matter. Today, baryon acoustic oscillations act like a cosmic measuring ruler, helping astronomers track expansion across time. Type ER supernovae offer yet another ruler, or more precisely, a standardizable candle. Because their brightness can be estimated, astronomers use them to measure distances across the universe. Observations of distant type ER supernovae in the late 1990s revealed that the expansion of the universe is accelerating, leading to the modern idea of dark energy. All these lines of evidence feed into the standard cosmological model, known as the lambda cold dark matter model. Lambda refers to the cosmological constant, the simplest model of dark energy. Cold dark matter refers to dark matter that moves slowly compared with the speed of light in the early universe, allowing structure to grow in the pattern we observe. The model also includes ordinary matter, radiation, cosmic expansion, early universe fluctuations, and the gravitational growth of galaxies in the cosmic web. It is not a complete theory of everything. It does not explain the particle nature of dark matter. It does not fully explain why dark energy has the value it appears to have. It does not tell us the total size or global topology of the universe, but it is remarkably successful at connecting many different observations into one coherent picture. Mathematical modelling then allows cosmologists to test possibilities. General relativity provides equations for how space-time evolves. The Friedmann equations describe how the expansion of the universe depends on matter, radiation, curvature, and dark energy. Computer simulations use these ideas to show how tiny early density variations could grow into galaxies, clusters, filaments, and voids. But modelling is not the same as direct observation. A model becomes powerful when it explains evidence and makes predictions that can be checked. It becomes weaker when it floats too far from what can be tested. This is where speculation enters carefully. The universe beyond our horizon cannot be directly observed. Its light has not reached us, and some regions may never be able to send signals to us at all. Still, cosmologists can infer likely properties beyond the horizon if the cosmological principle continues to hold. Since the observable universe appears broadly homogeneous and isotropic on very large scales, it is reasonable to expect that regions beyond our observable limit may contain more galaxies, more clusters, more voids, and more cosmic web. Reasonable does not mean directly proven. There is also cosmic variance. We observe one universe from one location. We cannot step outside the cosmos and compare many universes. We cannot sample the largest possible scales from many independent viewpoints. This limits how confidently we can know the total shape, size, and global structure of all reality. So honest cosmology speaks in layers of confidence. There is very strong evidence that the universe is expanding. There is very strong evidence for the cosmic microwave background and a hot early universe. There is strong evidence that dark matter shapes cosmic structure, even though its particle identity remains unknown. There is strong evidence that expansion is accelerating, though the nature of dark energy remains mysterious. There is good evidence that the observable universe is very close to spatially flat. There is weaker evidence about the exact global shape of the entire universe, because the whole may be far larger than what we can see. There is no confirmed evidence that space wraps around within the observable region, and multiverse ideas, bubble universes, many worlds, branches, and higher dimensional landscapes remain speculative. They may arise from serious theories, but seriousness is not the same as confirmation. This confidence scale is not a weakness. It is what makes the science trustworthy. The edge of the universe is not answered by pretending every possibility is equally proven. It is answered by separating what has reached us in light, what we infer from gravity and structure, what our best models explain, and what remains beyond present evidence. What we can measure tells us the observable universe is vast, expanding, ancient, structured, and filled with mysteries. What we can infer suggests that beyond our horizon there may be more of the same cosmic architecture, and what we can only speculate about reminds us that the edge of knowledge is not the end of reality, but the place where careful imagination must wait for evidence. The most likely answer is also the simplest one. Beyond the edge of the observable universe there is probably more universe. Not a wall, not a drop. Not a final surface where space ends and some outer darkness begins. Not a cosmic fence with reality on one side and a mysterious outside on the other. The safest scientific expectation is quieter than that, but also much larger. Beyond the region we can see there may simply be more space-time, more matter, more radiation, more dark matter, more galaxies, more voids, and more of the immense cosmic pattern continuing beyond our horizon. This does not mean we know the whole universe is infinite. It does not mean there are identical copies of Earth just beyond view. It does not mean every multiverse idea is confirmed. It means that, based on the evidence we have, the most conservative extrapolation is that the universe continues beyond the part whose light has reached us. That conclusion comes from several connected ideas. The first is the large-scale uniformity of the cosmos. On smaller scales, the universe is richly uneven. Matter gathers into planets, stars, galaxies, galaxy clusters, long filaments, and vast voids. It is not smooth in the way a calm lake is smooth. It is more like a landscape, full of structure, but with patterns that become statistically even when viewed from far enough away. On the largest observed scales, the universe appears broadly similar in every direction. This is the cosmological principle, the idea that the universe is homogeneous and isotropic when averaged over enormous distances. Homogeneous means similar from place to place. Isotropic means similar in every direction. The cosmic microwave background supports this picture powerfully. This ancient light fills the sky with nearly the same temperature in every direction, apart from tiny variations that later grew into galaxies and the cosmic web. It does not show one side of the universe looking like a boundary and the other side looking like a centre. It shows a cosmos that, at the earliest visible time, was remarkably uniform. The standard cosmological model also supports this. The lambda cold dark matter model describes a universe containing ordinary matter, dark energy, radiation, expansion, and early density fluctuations. It is not complete, and it leaves deep mysteries unsolved, but it successfully connects many observations: the cosmic microwave background, galaxy clustering, baryon acoustic oscillations, gravitational lensing, type IR supernovae, and the growth of a large-scale structure. When a model works across so many different kinds of evidence, it gives scientists a reason to trust its broad picture, while still remaining careful about its limits. So beyond our horizon, the simplest expectation is not a sudden change into nothingness. It is more of the same kind of cosmos, but more universe should not be misunderstood. It does not mean everything beyond the horizon must look exactly like our local region. The distribution of galaxies may be different in detail. There may be clusters larger or smaller than those we know. There may be rare objects we have never observed, simply because our observable patch is finite. There may be regions where density fluctuations happen to grow in slightly different ways, producing different arrangements of cosmic web, different voids, and different histories of star formation. If inflationary models are correct, the total universe may be vastly larger than the observable region. Some speculative versions even allow variations far beyond our horizon, perhaps in regions so distant that their conditions differ from ours in ways we cannot test. But that belongs to a less certain layer of the answer. The conservative answer remains, more space-time shaped by similar laws, not a confirmed doorway into exotic realms. No telescope can simply zoom past the observable edge. That limitation is not only technological. Better telescopes can reveal fainter galaxies, sharper details, and earlier cosmic structures. They can push back the limits of practical observation. But they cannot make light arrive before it has had time to travel. They cannot bypass the finite speed of light. They cannot ignore the expansion of space. They cannot see ordinary light from before the universe became transparent. The observable edge is built into cosmic history. It is like the horizon at sea. When you stand on a shore, the horizon does not prove that the ocean ends at that line. It shows the limit of your view. You may have excellent reasons to believe there is more ocean beyond it, even without seeing that farther water directly. But the horizon itself refuses to provide a postcard. The cosmic horizon is stranger, older, and deeper, but the lesson is similar. It is a boundary of visibility, not necessarily a boundary of existence. So the final answer must be layered. What we know is that the observable universe is vast, ancient, expanding, structured, and limited by horizons of light, time, and causality. What we infer is that beyond our observable edge, there is probably more universe continuing beyond our view. What remains beyond scientific reach, at least for now, is the full size, shape, and ultimate nature of all reality. The edge we see is real, but it is not known to be the end. So what lies beyond the edge of the universe? The answer depends on which edge we mean. There is the edge of the observable universe, the boundary of the region whose light has had enough time to reach us. There is the cosmic event horizon, the boundary beyond which events happening now may never send signals to us, because accelerated expansion carries those regions away too quickly. There is the edge of theory, where general relativity and quantum physics have not yet been joined into a complete description of the earliest universe. And there is the imagined edge of space itself, the wall or outer rim that human intuition so naturally pictures, but that modern cosmology has not found. The journey begins with that intuition. We're used to edges because our world is full of them. Rooms have walls, maps have borders, planets have surfaces, oceans have horizons. So it is natural to imagine the universe as a giant object with an outside. But the universe is not known to be an object sitting inside a larger space. In standard cosmology, it is space itself, together with time, matter, energy, radiation, dark matter, dark energy, and physical law. The observable universe has an edge because light is finite. The universe has a finite observable history, and the space has been expanding while light travels. Looking far away means looking back in time. The deepest ordinary light reaches us from the cosmic microwave background, released when the early universe cooled enough for neutral atoms to form about 380,000 years after the Big Bang. That ancient glow is not a wall in space. It is the surface of last scattering, the moment when the universe became transparent. Beyond that, there was still a universe, but not one visible through ordinary light. Cosmic expansion adds more subtlety. Distant galaxies can recede faster than light without breaking special relativity, because the space between us and them expands. Horizons then become boundaries of information, not physical fences. The particle horizon tells us what light could have reached us by now. The event horizon tells us what may ever be able to reach us. The Hubble sphere marks where recession due to expansion equals the speed of light, but it is not the same as the edge of all we can see. The shape of space remains partly uncertain. The observable universe appears very close to spatially flat, according to measurements of the cosmic microwave background, such as those made by the European Space Agency's Planck satellite. But flatness does not prove the whole universe is infinite. Cosmic topology could still be more complicated. Space might be infinite, or finite without an edge, or far larger than we can ever measure. Inflation suggests the visible universe may be only a tiny patch of a much larger whole. Dark energy suggests that some regions we can see in ancient light may never send us their present light. Extra dimensions, brains, quantum cosmology, eternal inflation, and multiverse ideas offer deeper possibilities, but they remain more speculative. So the clearest answer is also the most careful one. Beyond the edge of the observable universe, the most scientifically grounded expectation is more universe, more space-time, more matter and radiation, more cosmic web, galaxies, clusters, filaments, and voids shaped by similar laws. We cannot directly observe those regions, but the large-scale uniformity of the cosmos makes this the simplest extrapolation. There is no evidence for a physical wall, an outer darkness, or a literal drop-off where space ends. There is strong confidence in cosmic expansion and the observable universe. There is strong evidence for the cosmic microwave background and the hot, early universe. There is good evidence for large-scale uniformity and near flatness. There is uncertainty about total size and global topology. And there is speculation around eternal inflation, brains, and multiverse models. The edge of the universe may not be a place at all. It may be a horizon of light, a boundary of contact, or a limit of theory. And perhaps its deepest lesson is not that reality ends, but that reality is larger than the portion able to send its light to us.